So, as Philip said, I'm Ondřej Kijanek. I'm a research associate at the Institute of Computational Design and Construction in the University of Stuttgart. And our research is mainly concerning how to change building construction industry. We recently got or formed our excellence cluster in Germany, and big part of the research is actually about human-robot collaboration in construction in general, but my research is specifically about timber construction. So I briefly start with describing my research and why is it important, and then I'll jump into the KUKA Innovation Award and our project there. So timber construction is, or construction in general, is very specific type of industry because it's usually one kind of a production. So usually you are making just one of the buildings. Sometimes you are making modular buildings, but still usually it's tailored to the site itself. It has very fragmented supply chain because there's a lot of trades that are operating on site and so on, and it's mainly fabricated on site. The timber construction is a bit different, and it's solving some of those big problems because there is high degree of prefabrication. It's usually lightweight construction, but most of the companies are actually very, very small, and the importance of the craftsmanship and of the human sort of supervision is very important. So in order to bring construction industry and timber construction on the level to, let's say, well, automotive industry is maybe too high up, but let's say to Industry 4.0, it's important to enable access to advanced manufacturing techniques such as robot manufacturing. But classic robot manufacturing is not completely, it's not so good for construction in general, because to make classic robotic manufacturing cost effective, you have to have very high production rate and and therefore you are also having low degree of flexibility and high degree of sensitivity to disturbances. It's not problem only in construction, but it's problem in automotive industry nowadays as well, where, for example, Mercedes-Benz a couple of years ago lowered their amount of robots on production side and actually replaced them by humans. And the robotic companies are trying to react on that by boosting the human-robot collaboration, which means that the robot can actually work closely with the human together. There's no fencing usually, as you can see on the picture over here. However, it has a bit of a low payload, and it has very complex programming. So there is this another issue right now that, yes, we can work with robots, but to repurpose such a system is very complex. It's actually more complex than repurpose, not really hardware-wise, but like software-wise, and in terms of programming, it's actually harder to repurpose the new type of robots just because they are much more complex to program. So my research is about how to enable this, what type of interfaces do we need to interact with the robotic setup, how to repurpose the robots for the small and medium-sized companies fast enough, how to repurpose them for different construction projects and different projects in general. And then last summer, there was this call for the KUKA Innovation Award, and it was actually, we took the chance because we could prove some of our ideas and develop some of our ideas for and try to compete in this real-world interaction challenge. And we got selected to the 5 finalists, and we presented it at Hanover 2018, so about 4 months ago. And our proposal was to make a collaborative robotic workbench, where a small, intelligent robot would be commanded with very high-level commands. And then we were sort of looking for good interface and very intuitive way how to program and command this robot and how to also get the data of the system. And we figured out that probably the most intuitive one, which is still a new technology, but the most intuitive one would be an augmented reality, which we tried briefly, but not for robot programming. So we based our application about augmented reality interface with the robotic setup. But that was, of course, not the only thing we were doing. I will show you just a quick video that was actually done by Kuka, but it's fairly well explaining what we were doing. So our setup was building those very intricate spatial timber structures that were more or less impossible to build just by looking at plans and measuring things. Or, of course, it's not impossible. It would be possible, but it would mean that for each placement of those timber sticks, we would actually have to measure first at least 5 minutes, and there was, I think, 700 of those timber wooden beams. So it was much easier to do it by robot and to command it. As you could see, we had this augmented reality interface. We are using Microsoft HoloLens that was good enough for the application, but we discovered, as you can see, it's still the performance of the headset is still not perfect. We also had some other issues at the side. We had to use the public Wi-Fi and things like that. And for the sort of background, and here you can see the Forge viewer that I explained later how we were using it there. But for the background logic, we were actually using the robot operating system, which is pretty standard tool in robotics. That was providing the sequential offline path planning for the robot, because the idea was that the sort of the sequence of the construction was actually not pre-planned or anything, but it was controlled by the operator. So, just a minute. Okay, so to explain it closely, I'll show this little graph. So the whole idea was that there is some designer who was designing the structure in a classic CAD program, and then it's sending this information to a server actually that was storing this like abstract information, and then this information was used to show in the augmented reality what can be built in this precise moment, and the operator could basically choose which of the parts is able to, or like which of the part will be constructed next. And then the robot basically planned the path, pick the timber beam, and place it where was needed. It was just a demo, of course, but the offline path planning was very important because the robot or the system designer or anyone basically didn't know how the scene and how the environment will evolve for the robot. And those assemblies we were then placing to build the larger timber structure. And for that we actually needed to visualize it somehow. So here you can see the actual setup at Hannover Messe. So this Benedict is wearing the HoloLens and commanding the robot. I'm sort of supervising and everything goes well. And you can see the half-built assembly on the site. This is just how did it look. So the robot picked the beam, and then it was attached by the operator. So as I said, we had the CAD program that was uploading the stuff to the database, and then this whole thing was sort of enclosed in the robot operating system. As I said, it's not really operating system, it's sort of set of tools. It provided some communication and some time synchronization, and then one can write little scripts for communicating with various robots. It's very, very highly used in robotic research, and almost everyone is using it, I think. And this information was then streamed to the web server that was done in Forge, that was done there to provide a background diagnostic. The idea was that the designer was designing the building, then the operator or the constructor was constructing the timber structure, but then there was, of course, the sort of management or supervision level that was able to view it online wherever they were. This is how the augmented reality interface looked like later on, not the one that you saw in the video, where the blue ones were what sort of steps are available for the operator to execute as next. This one is the selected one, and here you can see the robot path, which was sometimes pretty crazy. The whole interface was built actually on the previous interface that we built with Three.js a long time ago when there was no Forge. So it's similar to the presentations that were here before. But then when we discovered that actually there is already available web interface to visualize all the data that we wanted, and which would simplify like greatly the way how we could do it, we designed our own little user interface, which was basically showing the built structure already. It was also showing the position of the HoloLens without the person, of course. And it was showing the movement or the animation of the robot in real time. So the Forge interface was actually communicating through WebSockets with the robot operating system, and it was providing all the sort of real-time system data that was needed to visualize there. So whenever this was loaded, the browser was communicating with the server that was serving those persistent data, so not the real time, like the position of the robot, but like what is built, what is on the bed, and so on and so forth. Visualizing it here, right now you can't see anything because I think it's the beginning of the next assembly here, and then showing basically the current time of the system. So if there was some time delay, it was shown here. The little information about what is going on, what was planned, what is happening in the system, the ID of the stick that is going to be picked, what is the robot doing right now, and so on and so forth. So in the end, because also Forge is built on Three.js, and we had some experience with that, it was actually quite easy for us to customize it as we need it, and provide the other sort of real-time WebSocket communication and animation of the robot and so on and so forth. Now we want to push it, so there's just a little discussion what we have to do to make, because this project is of course continuing, and we will get the robot again in the end of the year. And we want to also use the Forge viewer for another project that is right now running and which will be ready in the spring in 2019, which is building of this big timber shell, where we have this 2 robot setup, this time not with collaborative robots, but with real big robots. But because the process is very, very complicated, we anyway need some sort of interface or let's say supervision interface for the users, for us to see what is going on, what are the errors, and so on and so forth. And for that, we are now implementing another iteration of the Forge interface. Now, when we know it better, we also know how to make the things easier for ourselves. Okay, that's it. Thank you.